Thanks very much to the organisers. It's very nice to be back at CIRM again, back in the sun. So we'll be talking about establishment of a population in a new habitat. A habitat where initially the growth rate is negative, and so the only way the population can survive in the long run is by evolving a higher growth rate, evolving ultimately a positive growth rate. So this problem arises in various contexts. It's usually termed evolutionary rescue, the idea being that for one reason or another, individuals find themselves in a bad habitat, and the only way they can establish is by evolving increased fitness. But one can also think of the evolution of adaptation, let's say, to a new host plant. Let's say some herbivorous insect is living on one host plant, but a few individuals occasionally try out different plants. Initially a negative growth rate, but if they can establish a population with a positive growth rate, then we have a kind of model of sympatric speciation. So there's a lot of interest in these kinds of models, and of course one can simulate arbitrarily complicated situations, but we're trying to really simplify the problem down to its essence, and we're doing that by trying to identify key parameters which in principle, actually even in practice, could be measured. And we're therefore using a very simple, very robust model, the infinitesimal model. So what will happen is that Alison will now describe the model, the infinitesimal. I'll then come back and describe the way we apply it to the problem of establishment of a new population, evolutionary rescue. And then Alison will come back and describe some approximations, some pretty, well, should I say crude approximations? Okay, okay. So some diffusion approximations to the state of the population once it's established. So I should say that this work was published in TPB in a special memorial issue for Paul Joyce, who actually came to the first meeting here, I remember, has very much missed. There's also a paper which describes, probably at inordinate length, the infinitesimal model, its history and justification and so on, also in TPB recently. Okay, so Alison.
Okay, so we didn't check if this microphone works, so let's hope it does. And we didn't check if I could operate the machinery. There we go. Yeah, those of you who are veterans will know that any conference that Anton Vakolbinger is involved in the organisation of, that Nick and I are both at, we end up with this comedy double act halfway through. So I am indeed going to talk about the infinitesimal model, which is actually what our last comedy double act was about. And this thing doesn't seem to advance the slides, but presumably a spacebar does. Yay. Okay, so here's the infinitesimal model.
Alison,
and it's most...
turn it on. That helps.
Oh, how?
Yes. With the button.
We're not really compatible technologically, me and Nick. No, dankeschön. Okay. And then one of these buttons will do something horrendous, and one will operate the pointer. Yeah, this one does something horrendous. Okay. So here's the basic model. The basic model is that we're interested in a trait value, and that trait value has two components. It's got a genetic component that I'm going to denote by capital Z, and a non-genetic component, which actually today we're going to ignore, but which is nonetheless important, and turned out to be very important for the mathematics in the long discussion of the infinitesimal model that we had last time. So what the infinitesimal model says is that if I take two parents whose trait values are Z1 and Z2, then their offspring, the distribution of the trait among the offspring is normal, with mean Z1 plus Z2 over 2, so the mean trait value of the parents, and some variance V0. And in a large outcrossing population, that variance is going to be constant, and otherwise, as we'll see a little bit later on, it will decrease in proportion to the relatedness between those parents. Okay, so let's just look at the very simplest case. So I should say that the infinitesimal model is not something on which, as far as I can tell, people can really agree a definition, and therefore they can't really agree its origin. But so I'm just going to pick my sort of favourite historical figure and attribute it to Fisher. I think it's fair to say it is in Fisher. It's not terribly easy to find in Fisher, but I think it's fair to say it's there. So here's a simple case, and this was an example that was worked out by Bulmer. So suppose we've got a large outcrossing population, and suppose it's just mating randomly. So I've got some neutral trait, and individuals are just choosing two parents uniformly at random from that population. Then very rapidly, the distribution of the trait across the whole population will actually evolve to a Gaussian. And in this outcrossing population, in which, remember, V0 was the variance of the offspring of just two individuals, the variance across the whole population will just be twice V0. And let's see why that might be. I'm going to have to work out which of these buttons operates. There we go. So let's suppose that the variance in the parental population is V1. Then looking at Z1 plus Z2 over 2, I've sampled two individuals uniformly at random from the previous generation. So the variance coming from there is going to be a half V1. That's what we're getting here. And then I've got the variance that's generated by the reproduction. So this is the released during reproduction between the two parents. That's V0. And if I'm at stationarity, then V1 is equal to V1 over 2 plus V0. And that tells me that V1 is twice V0. And you immediately see something interesting and perhaps surprising, which is that across that population, half of the variance we're observing is actually within the families, and half is between the families. And that's, I think, a rather important fact for what follows, actually. Okay, however, in general, what we're going to call the infinitesimal model only says that the genetic components within families are normally distributed. It doesn't say anything about the distribution of the trait value across the whole population. We will make that assumption, but it's important to note that, and Nick's very impressed that I've discovered how to do red block capitals. The distribution across the whole population may be very far from normal, and we'll see why that might be as well. Okay. So the key ingredient in the infinitesimal model is the pedigree. So let's talk about pedigrees for a little bit. So each individual in our population has got two parents. So here's the population in the present day. And each of them has picked two parents, not necessarily uniformly at random. There's some model underlying this which says how those parents are picked. They might be picked according to trait value. There might be some selection going on. But what's important for our purposes is that each individual has two parents, and I'm going to trace back the ancestry of each individual. So, for example, this guy had this parent and this parent. And if you look at this carefully, what I've done is I've identified all the descendants of this individual in the ancestral population, and you see, well, that's everybody now. And some individuals, of course, have no descendants. I find these pictures hard to draw, so it's a bit of a cheat. This one didn't have any descendants at all. But there are also individuals who don't leave anyone in the current population. We're going to allow selfing, so this parent was picked twice by this individual. Now, before we move on to pedigrees in general, I think it's an interesting aside to think about pedigrees a little bit. In fact, maybe it's worth just looking at this picture for a moment more. If I think about this individual, and think about someone sitting up here, let's say individual number 2, there are multiple different routes through this pedigree that join this descendant from this ancestor. Right? There are lots of different ways I could have followed blue lines up and got to there. And that's important for the models that follow. Okay, so here are some important, some cute observations, I think I'd say. So there's a paper due to Chang in 1999, which just gives us an idea about what the timescale is over which pedigrees evolve. So what's the appropriate timescale for pedigrees? Well, he was considering a diploid right Fisher model, so that means my population size is fixed, and the parents are picked uniformly at random with replacement from the previous generation. So that's a sort of Bulmer setting. And then it turns out that if you ask how long do I have to trace back before I find somebody in the ancestral population who is ancestral to everybody alive now, and I call that tau n, then tau n is essentially log 2n. Okay? More surprising still, actually, that's not so surprising. This is more surprising. If you go back 1.77 log 2n generations, then all the ancestors you see are either ancestral to everybody in the present-day population or to nobody. Right? This is in sharp contrast to what we see when we think about classical population genetics. You've seen already in several talks that the appropriate timescale for a Kingman coalescent is n generations. If I'm looking at genetic ancestry, it takes n generations to decide when Nick and I had our most recent common gene at a particular locus. Actually much longer, I don't think we're that closely related. Okay. And the reason that the pedigree and the genetic ancestry are so different is that this thing is, we already pointed out, that there are many, many routes through the pedigree from the ancestor to the present, and there's no reason why any particular ancestor in my pedigree has actually contributed any genetic material to me. Okay? All right, so back to pedigrees in general. So one way to represent a pedigree is a matrix. So here I've taken part of the previous picture. This was the present, my population of size 5. And what we do is that we represent for each individual alive in the present, there'll be a row in my matrix, and it will specify who the parents of that individual are in the previous generation. So for example, individual 1 had parents that were labeled 1 and 3 in the previous generation. And so I put a half here and a half here. So this is the first slot and the third slot, and 0 is elsewhere. And this is just encoding Mendelian inheritance. It says if I look at a locus, what is the probability that gene was inherited from the individual labeled 1 in the previous generation? Well, it's a half. It certainly wasn't inherited from the individual labeled 0, because that's not even in my pedigree. And probability a half, it came from the individuals labeled 3 and 0 and 0. Okay, so it's just encoding the Mendelian inheritance. It's important to note that laziness has actually shone through here. The population size does not need to be constant, but I happen to have this picture already drawn for constant population size. But there's no earthly reason why there shouldn't, for example, be a 6th individual over here. I just wouldn't get square matrices any longer. Okay, and when there's selfing, what do we do when we've allowed selfing? Well, we allowed selfing in our previous picture, so here was 3 generations in the past, and this individual was produced by selfing, and that's just represented by putting a 1 in the corresponding slot in my matrix, because with probability 1, this individual inherited its genetic material from the individual labeled 1. Okay. Now, what's going to be a key ingredient is what is the probability that if I take 2 individuals, now let's suppose they've got labels I and J, from my population in generation T, what's the probability that the homologous genes in those individuals were actually descended from the same ancestral gene? Because we said there are many, many routes that the genetic descendants can pass through our pedigree, and what's the probability that actually these guys come from the same ancestral gene? And that's easy in terms of these pedigree matrices. So the probability that a gene in I and a gene in J come from the same ancestral gene, well, I ask where did the gene in I come from in the previous generation? That's given by, the probability it came from K is given by MIK of T. Where did the gene from J come from? Well, that's given by MJL of T, tells me those probabilities. And if I came from K and J came from L, then in order for them to be from the common ancestor now, those genes in K and L must have come from a common ancestor. And K and L lived in generation T minus 1, and so we arrive at this recursion. In the diploid case, we write down a corresponding recursion for if we sample the 2 genes, so you've got 2 genes in each individual, and if we pick those uniformly at random, we write down the corresponding recursion, and probability a half, when I do that, I pick the same gene, and that's why I get a 1 here. But let's concentrate on the haploid case, because it's easier without all those stars. Okay, so there's a simple recursion which tells me if I sample 2 genes from individuals, 1 from individual I and 1 from individual J at time t, 2 homologous genes, what's the probability that they were inherited from the same ancestor? Okay. Right, so that's told us about pedigrees, and the pedigree gives us this key information about inheritance, the probability of genes being inherited from the same place. And what we're going to do is we're going to write P of t for the pedigree relationships between everyone up to and including generation T. And I'm going to write Z of T for the traits of all the individuals in the pedigree up to and including the Tth generation. And what the infinitesimal model tells us is that if I look at the trait values in generation T, conditional on knowing the entire pedigree and all the traits up until the parental generation, then that's a multivariate normal. So notice again, it's a statement about the distribution within families, not across the whole population. And in particular, the population doesn't need to be neutral. That pedigree could have arrived in any way you like. It could be an artificial breeder. It could be that you went to buy yourself a show dog and you looked at the pedigree of all of the, if you go and buy a dog, I'm told, you can get a pedigree of the parents. You won't yet know the trait value of your puppy, but you know the trait values of the parents. You know their entire pedigree, and what the infinitesimal model tells you is that the trait of your dog, of your puppy when it's born, will be a normally distributed random variable, and it will be determined as the mean value of that trait in the parent and a variance, and we're now going to specify what that variance is. But in particular, the pedigree is capturing the fact that almost certainly a lot of selection has gone on to produce that pedigree. In a wild population, we might have some sort of population structure. It might be capturing the fact that individuals live in different places. There's a lot of things that can be encoded in that thing, the pedigree, but still we're going to get normally distributed traits within families.
Alison?
Yeah.
There's some things maybe not said in that slide. So if there were
possibly,
if there was like a line of two individuals self or
okay, so we'll
sample those two.
Yeah, that doesn't so we're going to come back. We're going to come back.
It wouldn't be normal. It wouldn't be normal.
That's correct.
Right.
Yeah, so if you've got too much inbreeding, you lose normality completely. And we're going to see what you have, the sort of restrictions that you have to put in place. In fact, I didn't want to go into the gory details of the long infinitesimal paper, which I'm sure you've perused every formula of in great detail, John. So I will sort of explain the kind of conditions without being too specific. But yeah, John's absolutely right. You don't want a pedigree that's too special. And we'll see why. We'll see what that means, what too special means. Okay, so let's think about why it might be a reasonable model. So I'm going to do the simplest thing, and again, this isn't really necessary, but I'm going to think about additive traits in haploids, no mutation. And I'm going to suppose that my trait is determined by M unlinked loci, right? So they're just going to be passed down independently through that pedigree using Mendelian inheritance. And the trait value in individual J is then going to be expressed as Zj, which is a normalizing constant. This is actually going to be the average value of the trait in our ancestral population, for convenience reasons. And then I'm going to suppose that there are contributions. So this is individual J, locus L. And the contribution from the allelic state in that individual at locus L is going to be 1 over root M times this scaled contribution eta JL. So all the contributions are very small, but there are a lot of them. And when I add them all up, that's going to give me my trait value. And in the ancestral population, because of this normalization, taking out the Z0 bar, I can suppose that these eta JLs, I'm going to denote it by eta JL hat in the ancestral population, are mean 0. And for convenience, I'm just going to suppose that they're IID. I'm going to suppose my ancestral population is unrelated. It's not, again, it's not vital, but it's just convenient. But now you can sort of see, I mean, let's suppose we looked at the ancestral population and we asked about a trait. So then these things here would be IID. Well, then the central limit theorem tells me that this is going to be a normally distributed random variable, right? At least under reasonable conditions. My eta JLs mustn't get too big. Okay. But under very general conditions, my trait value will be normally distributed. Okay, but to have a look at the trait now, we need to understand how reproduction is going to work in this context. So for a particular individual, I'm going to use 1 with a box around it and 2 with a box around it to refer to their first and second parents. And so, for example, eta JL with a 1 is the scaled allelic effect at locus L in the first parent of the jth individual, which is a bit of a mouthful, but I hope you can sort of see what it is. And similarly, I would write ZJ1 for the trait value of the first parent of individual J. And now Mendelian inheritance just says, well, the probability that the allele at locus L in the jth individual was inherited from the first parent is 1/2. And from the second parent is 1/2. Okay, so, and I'm going to encode that with this Bernoulli random variable. And so when I look at the trait in my offspring, it's the Z0 bar, this normalizing constant, the 1 over root n, sum 1 to n. And now this is going to be 1 if I inherited from the first parent, and this is going to be 1 if I inherited from the second parent. Okay. Right, so that's just the same thing. I've just written the same thing down over here. And what we want to know is the distribution of trait values in generation T, conditional on knowing this whole pedigree and the trait values up until the parental generation. In order to do that, I need to know what these things are going to look like if I condition on knowing all the trait values up until ZT minus 1. And what underlies the infinitesimal model is that conditional on knowing the pedigree and these trait values, I don't actually learn anything. I learn very little about this allelic state at a particular locus. Okay. Let's suppose that we can, I'll try and convince you that's true on the next slide, but let's think about what this will bring us. So suppose that I can prove this. Suppose that I can convince you that the distribution of this guy is not really affected by knowing the trait values in the parents. Well then, if I try to calculate the variance of the offspring of these guys, the parents that I've labelled 1 and 2, well, I need to be able to calculate e to jl1 minus e to jl2 squared, right? Well, these are the same if the genes were inherited from the same ancestor, because we're in this haploid setting, and that had probability just F1, 2. This just means probability of identity of the parents labelled 1 and 2. And if they were inherited from different individuals in the ancestral population, well, this is just e to jl hat. I mean, it's 2 independent samples from e to j hat, if you like. And I'm looking at the difference of them squared, so that's just twice the variance in the original population. So what we see is that the variance among offspring is reduced by this factor. Right? So the probability of identity is actually telling us that's all the information we need. That and the variance in the ancestral population is all the information we need to determine the variance among the offspring of individuals in generation T. So provided I can convince you that this is true, that knowing all the traits up to generation T minus 1 doesn't really tell me much about individual allelic states, then we've got the infinitesimal model. We see that the trait Cj will be normally distributed around the mean of the parents. So if you just normalize this by taking out the mean of the parents, so you take out half of that, and you're going to be left with a sum of things of this form, and the variance is going to be 1 minus F12 times the variance in the ancestral population. Okay, so why is it that we're not really gaining any information about the allelic state at locus L when we observe the trait? And this is a toy example. This is actually due to Fisher, one of the cruelest things. Nick's not naturally a cruel person, I should say. I try and say something nice about him. But he occasionally has streaks of cruelty. And one of them was to present me with sort of the complete works of Fisher and say, find that argument, it's in there somewhere. After a week at IST, I found it. So here's how it works. So let's suppose, for simplicity, these e to L are IID, and they just take values plus or minus 1 with equal probability, and Z0 buys just 0. So if I know that my trait value is equal to k over root m, what does that tell me about e to 1? Right? So remember how the trait value is set up. I add up the traits at all the different loci, and I divide by the square root of m. So that's why I've left it in this form, k over root m. Well, just using Bayes' rule, I write this the other way around, right? So that's what's the probability that the trait is equal to k over root m, so that's the sum of the e to l's is equal to k, given that the first locus takes the value 1, times the probability the first locus takes value 1, divided by the probability the trait was k. And in this case, you can just work it out. You just write it down. And I'm not going to take you through this, because I think that would be a bit insulting, but the binomial coefficients, almost everything cancels, and what you end up with is 1 plus k over m times your underlying probability, your unconditional probability that e to 1 equals 1. So, provided k over m is small, I've not actually gained very much information about the value of e to 1. Okay. So that's the same thing written again. So what's a typical trait value? Well, for a typical trait value, z is going to be order 1. So k over m, this correction, is going to be on the order of 1 over root m. Okay. And so, actually, apart from when the trait values are really extreme, which will give us k over m on the order of 1, so if k is plus or minus m, that's actually telling me, that's giving me complete information about all the alleles. So if I pick extreme alleles, I'm obviously going to get complete information. If k is m, that's because all of the etas are 1, and so e to 1 must be 1. If k is minus m, they're all minus 1, so e to 1 must be minus 1. But if I'm not taking extreme traits, then I'm going to get an error of this order. I've realized I forgot to say something about John's question. John asked about what happens if you get lots and lots of selfing, and the answer is that this quantity goes to 0, and you lose the variance, and your infinitesimal model breaks down. Okay. So what we see is that the infinitesimal model is looking good, provided we don't choose very extreme values of our trait and we don't choose a very extreme pedigree, so those Fij's are reasonable values. And what's happening is that for a typical trait value, there are so many different configurations of the allelic effects of those eta i's that correspond to the same trait value, that if you tell me the trait value, I still don't know which of those very many configurations it is, so I'm not getting much information. Okay, so what the infinitesimal model says, again, is that conditional on knowing the pedigree and all the trait values in that pedigree up until the parental generation, so the pedigree all the way up to the present, trait values up to the previous generation, if I look at the distribution of the trait value of individual j minus the mean value of its parents, and I do that for all j equals 1 up to the current population size, then that will converge as m, as the number of loci goes to infinity, to a mean zero multivariate normal, whose covariance matrix is actually diagonal, and what are the entries on the diagonal? Well, that's this segregation variance, as we call it, so it's this 1 minus Fij times the variance in our ancestral population. So it's how much variation is reduced by the parents of individual j reproducing. Nick? Oh. Should have had an alarm for you.
Yeah. Okay, so back to the original question, which was how can a population establish, given that it initially has a negative growth rate, it has to evolve a positive growth rate. And what we do, the crucial step, is to represent the genetic variance in growth rate in the new population, in the new habitat, by the infinitesimal model. So we have a very simple model which summarizes all of the different components of fitness. All that matters in the end is the growth rate of the population, and we treat that as an additive trait. So what I'll be doing is, first of all, considering a single individual, right? And we assume that we have random mating, including selfing. If we don't have selfing, then that single individual is kind of doomed. So that individual produces offspring, and offspring, and offspring, and they reproduce according to the infinitesimal model. And we ask, what's the chance that the population will actually get established? Now, we're ignoring all kinds of complications by just focusing on the initial establishment of the population to begin with. So we ignore interactions between individuals through density regulation. We assume directional selection on the trait, being fitness. There might be some kind of stabilizing selection or something at some stage on this sort of hypothetical trait we're looking at. But for the moment, we'll treat the trait as essentially fitness. Right? Now, this looks something like a branching process, and one might hope, in fact, I think I initially foolishly hoped one might make some kind of mathematical, analytical progress with this, but it's not a branching process because there is an interaction between individuals in that they have to mate, they're reproducing sexually. And that makes it fundamentally different. It's actually a really interesting problem, I think, but one on which I think it's fair to say we fail to make any real progress in terms of getting analytical formulae, although we can make some approximations once the population gets a bit bigger. Okay, so we'll start by looking at the case of a single individual coming in. And then I'll look at the case where we have steady migration. So now we have individuals coming in at a constant rate. And there, of course, the population will eventually, establish itself in some way. And we look at the expected time to establishment. Now, by establishment here, I actually mean growth to a very, very large number. And as I'm stating the problem so far, ignoring density regulation, assuming directional selection, at some point the population will blow up. So we're looking at the expected time to that blow up. Yeah. Yeah. Yes. Well, even if with a single individual, you can think about a single individual.
Remember that the variability that we're going to get released in the first round is half the variance in the
Yeah. Yeah.
representative normality from the source population inside would be promising.
So even if you have one or a few individuals, the infinitesimal model is simply making a statement about the distribution of trait values of offspring. And that will hold as long as there's not too much inbreeding. It is true that this is a slightly delicate question because I think this came up in a question to one of the talks yesterday that, you know, of course there is heavy inbreeding. So we are assuming that there's enough variability, there are enough loci underlying the trait that there's not so much inbreeding that the whole thing breaks down. But you know, I think that actually isn't unreasonable as long as there are, let's say, hundreds of loci involved. Because then, as Alison said, there's a lot of variability which is essentially held in those loci that are heterozygous within an individual, or if we're thinking about, you know, two individuals, when they come together, there will be a lot of heterozygous loci, and that, if you like, is hiding a lot of variability and actually half the variance in the population on average. Okay, so start with a single individual asking the chance that it will found a population of some sort. Then we ask about steady migration, and at some point it's inevitable that the population will get established at large numbers, and we ask about the expected time for that to happen. And then I'll hand back to Alison and she'll talk about various ways of thinking about the stationary distribution of the population once we're in this established phase. So, to be more specific about what the model actually is, firstly, I said that we'd be dealing with the growth rate. Actually, it's convenient to think of a trait Z, and in the initial part of the analysis, we'll treat selection as acting purely as directional selection, and we'll treat the fitness essentially depending on a factor beta, which is a selection gradient, times Z. And specifically, we'll assume that the number of offspring is proportional to e to the beta z. Okay, so it's a discrete model, and actually the results will be largely in this section of the talk simulation results, and we simply simulate by saying that each individual or each pair will have offspring in proportion to e to the beta z. Okay, under the infinitesimal model, as Alison explained, offspring have a mean at the average of the two parents, and their value, their genetic value, is normally distributed with variance a constant, v, which is a characteristic of the source population where the individuals came from, times 1 minus f. Okay. And we're assuming some sort of very large source population with a fixed additive genetic variance 2v, meaning that the segregation variance within a family within that population will be this quantity v. And I'll be actually assuming, and in the simulations we'll be simulating diploid parents. Actually, the model looks very similar. We treat identity coefficients only slightly differently. The model is essentially similar whether we're thinking about tracking diploids or tracking haploids. Yeah, yeah.
Because if you've got a single individual and it's diploid, then actually the property of identity is not one just because you're going through that and you're putting a half. So that's
yes.
why we're going to get
Yeah. And in fact, in order for this to make sense and have a single individual able to found the population, we have to be tracking diploids because a single haploid doesn't have any variation, so it doesn't make any sense. Okay, so first of all then, we'll look at a single realization of this process. I should say that throughout, we're really simplifying things by assuming random mating. We assume that selfing is possible. Indeed, an individual is as likely to choose two parents the same, if you like, in a Wright-Fisher context, as two different parents, that there's a Wright-Fisher model. That's a very specific assumption. One could, of course, change that. To my mind, the most serious sort of gap in the model is that we ignore inbreeding depression, which of course is really important in practice. And what we are going to solve before the end of the year, apparently is the plan, is how to extend the infinitesimal model to include dominance, therefore to allow for inbreeding depression, and hopefully apply that to this model. But that's what? Okay. It's all done. It's done somewhere in our heads. Yes, it has to be written down. Okay. So for the moment, it's purely additive, and actually, to a biologist, that makes it all seem, clearly one would want to include a variable rate of selfing, some level of inbreeding depression. But still. Okay, so let's look at a particular example here. And the key point to me that comes out of this is not so much the particular simulation results as the fact that there are really just two parameters. I'll be throughout scaling everything relative to the additive genetic variance for growth rate, for the trait Z in the source population, which we set to 1. And then there are two things that matter. One is the mean Z in the source population, which in this example is -2. In other words, a population has to move 2 standard deviations in order to get a positive growth rate. It has to improve its mean fitness by 2 standard deviations. And then beta is a measure of the strength of selection. One can either think of it as a strength of a selection gradient on this trait Z, or one can think of it as describing the additive variance in fitness in growth rate in the source population when measured in the new environment. So the number of offspring is e to the beta Z. Z has, by definition, a standard deviation of 1 in the source population. Here, beta is 0.25. And to put that in context, this should actually read e to the beta Z naught. I don't know why I got a typo there. But if we take the average fitness of an individual in the source population measured in the new habitat, it's 0.61. In other words, the population will decline by a factor of 0.61 every generation. So it's got to do better. Okay, so we throw in a single individual. Sorry, yeah.
Not sure I'm understanding. So beta, you said, is like additive genetic variance. It also makes selection less effective.
So I'm treating an additive trait Z with a variance, additive genetic variance 1 in the source population. One can think of beta as a selection gradient on that trait. One can also say the additive variance for growth rate in the source population is beta squared V, or 2 beta squared V.
So beta equal to 1 would be the strongest selection in the new environment?
No, it could be arbitrarily large, and then you could have an arbitrarily large variance in fitness.
So think of...
It's true, sorry, smaller beta means less effective selection.
Yes, yes. Beta is 0, it's neutral. E to the plus beta Z, yeah.
And I guess I'm wondering where that comes from. Like previously, Alison, you said we're ignoring environmental variance, right, early on.
Yes.
So this is selection. So
this is selection
acting on the trait. And if you think about, you could even think of this as what's happening if I'm trying to get to some sort of stabilizing limit. That's just the first approximation. So but we're doing it as if it were directional selection, as if the bigger your trait, the fitter you are. Right? So the more offspring you're going to produce. So think of an individual with trait Z as producing on the average a Poisson number of offspring with parameter into the beta Z.
Great.
I guess you might be thinking...
Why do you want beta?
Sorry?
Why do you want beta?
Well, okay. Maybe it was a mistake. Maybe it's confusing things. I mean, we could have said that we just work with growth rate, and then we would just tune this parameter, the variance in growth rate, and that would be beta squared. That might have been simpler. The reason, actually, there is a reason for working with the trait, and that is that I want to move to a situation where I do stabilizing selection on the trait, because if we just have directional selection on the trait, everything blows up, and there's no equilibrium. So we'll go to move on to say, actually, there's a new optimum for this trait. When we're in this initial establishment regime, it looks directional, so this is fine, but we will eventually get to a situation where it stabilizes. Yeah. Okay. Okay, so we have this single realization. Here I'm plotting the blue dots are the actual values, the genetic values of each individual in the population. We start with one individual with a value of -2, and it has one offspring with a value which luckily has a genetic value of -0.7 or whatever, and so on. And towards the end, we have a whole lot of individuals which have value clustering around there, say. And crucially, this is a positive value, so the population now has an expected increase growth rate. And correspondingly, the population size goes from 1, diddles around, and takes off and grows more or less exponentially. So what's happening to genetic variance here? Well, it's starting as V equals actually a half. We're scaling it as 2V equals 1 because the total variance in the source population is scaled as 1. And what we expect to happen is that the genetic variance will decrease as 1 minus the mean inbreeding coefficient. the segregation variance, I should say, V, should decrease as 1 minus f bar, and one can work out what that is just from the numbers in the population. So we take these population sizes and multiply by 1 minus 1 over 2n, whatever, and we get this blue curve. That's the expectation. The actual segregation variance in the population will depend on the actual mean inbreeding, which is this, there's some other little wiggly blue curve. That depends on the random pedigree, so it's not quite this. And the actual variance of the z values, that's the variance of these blue dots, will be something different again, because there's a random process of generating the offspring. And that's this black wiggly line. So you can see that the variance in the population is declining very substantially. It's not quite going to zero. There is some residual variation at the end. And the main stochasticity in the whole process is how much inbreeding there is. And that will, of course, that will affect how the population can keep adapting. Although this looks flat, there is some genetic variance there. It is going to gradually do better. And eventually, actually, under this model, it will blow up. But it takes a very long time because we've lost most of the variance in this bottleneck. Okay? So that's just one realization. So the next step is to do replicates. I'm usually against doing replicates, but I do bring myself to do replicates. It just so we just run lots of runs with different values of the z bar of the source population. That is, how many standard deviations in terms of trait value below the mean is the original source? How many standard deviations does it have to increase in order to get a positive growth rate? And on this axis, on a log scale, is the probability that that individual will found a population that takes off and eventually blows up. These different lines show different values of beta, going from very weak selection up to stronger selection. That makes less difference than the number of standard deviations below. It makes some difference. Basically, if you have a larger beta, then there's more opportunity for selection to improve the growth rate. So the probability increases. And what you can see basically is that the probability of establishment goes to a very low value if it's more than 2 or 3 standard deviations below the source. This is the value of, I should say this value is the value of the single individual that you're putting in. Okay, so this seems very straightforward. This rather complicated diagram, I like complicated diagrams, is now asking not what is the probability that a single individual with a certain value will establish a population, but rather what's the chance that if you take a random individual from the source population, it'll establish. And that's a different question because you now get, if you like, 2 boosts. One is you may by chance get a particularly fit individual from the source population. And in fact, even if there's no selection, there's some chance that it will establish because it might just be above that threshold. And secondly, there'll then be the improvement in the offspring due to selection. So what are all these curves? Well, sorry, yeah.
May I come back again to these questions of the significance of the parameters, the beta and so on? Right. So you came up with these curves, right?
Yep,
that come from simulations, and
yes.
And Alison pointed to some possibility of using Poissonian offspring, right? In order to, and so I'm curious what these simulations, how they came precisely about. I mean, what are your, your generations?
Alison asked this, but yes. So the point.
Did you already put in the mathematical idealization, or did you come up with some, say, effective population size in which you do
the simulations are simulating exactly the model I stated.
Okay.
So we have, at any generation you have a list of individuals which are characterized simply by their Z1, Z2 up to Zn. Okay. You also have to keep track, not just of this vector of Zs, but of a matrix of identity coefficients. And we actually had, before one of the previous slides, a recursion for the matrix of identity coefficients, and that's crucial. So what we then do is say, for a particular...
What's the format of this matrix? I mean, how many...
N by N. N by N.
What's the N?
Population size. So you've got 3 individuals.
What did you take? for the population?
So initially it's one individual with one diploid individual with zero inbreeding. The two genes are unrelated. Okay. And then it might have, let's say, two offspring. And now you have a 2x2 matrix, which tells you how those offspring are related to each other, and you keep propagating this forward.
So that's evolving, that's growing in time.
Yes.
That was one of my...
That's right. And so this F bar here is a stochastic fluctuation in the inbreeding coefficients, which arises from the structure of the pedigree. If you know the pedigree, you know the inbreeding coefficients.
Right.
Yeah.
So that's some object built into the simulation. That growing population.
That's right. So when you do the simulations, you're tracking the vector of values. That's obvious. But less obvious is you're tracking the matrix of identities. You have to do that. And you need to do that because that matrix of identities tells you what the variability amongst the offspring of a particular mating is going to be. So the individuals produce a number of offspring which depends on their fitness E to the B to Z, and you choose them proportional to that. Then their offspring will have a normal distribution of values that you pick, which has a variance determined by 1 minus f. Yeah. Okay. Yeah. So it is a precise simulation of this idealized model. Yes. Okay. Okay. So that fortunately distracted us from this rather complicated diagram, but I'll try and explain this. So this is going from asking about the probability of establishment from a single individual with a particular Z to asking about what happens if you draw an individual at random from a population. Okay, so these lines here are the same as these lines here. I'm just picking out two values of beta, 0.25 and 2. So this line and this line correspond to this line and this line. Okay, they're the same. This is the probability of establishment given that you take an individual with -3, -2, -1 standard deviations, and it drops rather rapidly. This solid dotted line is what the probability of establishment if you take a random individual from a population with mean whatever, and now you've got a reasonable chance of establishing even if you're 4 standard deviations below. And basically that's because you've got some chance of, being, let's say, 2 standard deviations above the mean of the population, and then you can gain another 2 standard deviations by selection. So in some sense, there's a rather similar contribution of luck in getting a particularly fit individual as the migrant, and then selection improving it. Okay, and so the sort of rule of thumb then would be that you've got a reasonable chance of establishment, 10 to minus 4, 10 to minus 3, if you're, 4 standard deviations below. And that will depend to some degree on the strength of selection. Okay. Just as a comparison, these grey dotted lines are what happens if you do the same thing, but you turn off selection by choosing homozygous individuals. So their offspring are then identical. And now you get something pretty close to that. And then these lines are what actually you get if you have a sort of standard branching process calculation and you take an individual with a growth rate, let's say, if it has growth rate 0, it's got 0 chance of establishing. If it's got a positive growth rate and all its offspring have a positive growth rate, then the branching process calculation gives you the probability of establishment. So all this is sort of comparing, if you like, or trying to dissect the different components that are working towards the overall establishment probability of a single migrant coming at random from this source population, which is these pair of lines. Okay. So now we move on to another layer of complication, which is to say now we actually have migrants coming in at a rate big M. In other words, a Poisson number of migrants mean big M per generation. And we have then an expected time until the population gets established. Now, this lower limit here is simply the waiting time for a migrant to arrive. Here we've got big M, and this is just 1 over M. It's the expected time until the first migrant arrives. So it's got to take longer than that. Here, these dotted lines are what would happen if you just extrapolate from the single individual stuff that I just explained. And there, T-bar is simply 1 over the probability of establishment of any one migrant. So that's these lines. So this all sort of fits. These different lines are different values of the mean in the source population, -1, -2, up to -3.5. Okay, so it's getting steadily, the migrants coming in are from a worse and worse adapted population. So it's getting harder and harder, waiting longer and longer to establish. But what's going on here? We've got a kind of bifurcation here. And in fact, at a value of source means ES of 1.57, there seems to be a dichotomy. If the source population is not too different, if the mean is less than 1.57 standard deviations for this selection strength, then, as you include more and more migrants, eventually the thing will take off. It's fine. But here, you get to a situation where it actually starts to get harder and harder. The more migrants, the longer it takes to establish. What's going on? What happens is, sorry?
Clonal interference.
No. We're not having any of this complicated genetics. It's the infinitesimal model. So, yeah. What's happening is that there's another role of migrant. Obviously, you need migration in order to actually establish the population. That's this regime. But once migrants are coming in at a high rate, they are mating with the individuals in the new population who are struggling to adapt, but they're coming from this really badly adapted population. So they're pulling it back. So there's a swamping effect. If there's too much migration, the migrants come in and they pull the mean back and they prevent it adapting to a positive growth rate. So down here, there will actually, up here, I should say, with a badly adapted source population and a high migration rate, there will be individuals in the new habitat, but there will be a sink population. They'll have a negative growth rate and they'll be sustained solely by migration. So I'm counting here the expected time to establishment to actually a population growing to an indefinitely large number. And that becomes infinite as the migration rate goes up, if the migrants are just too hopeless, right? Okay.
So just an entropic effect.
I wouldn't say entropic. It's simply it's mating with something that's too badly adapted, produces offspring that are going to be, on average, halfway back to where they were. So you're out here. There's too many of them, too many coming in. Yeah. Okay, so.
That's nice.
All right, it's over to you. Yes. Okay, so Alison will now make everything become clear. Yes.
No, there's a mystery in that. Okay, so just in case we need a recap of Nick's model from before all those beautiful pictures, we had a large source population. The trait values in our source population we take to be normally distributed with mean ZS bar and a variance twice V, and Nick scaled that to be 1. In each generation, so we're going to consider now not just a single individual trying to establish, we're going to consider this constant migration regime. So in each generation, we're going to suppose that M unrelated migrants enter the population. And we're going to write N of T for the population size in generation T. So this is in our new population. The source population is essentially infinite. And Z bar of T will be the mean trait value in this new establishing population. And before migrants arrive, the number in the next generation, so the number of descendants of these N of T individuals before the migrants come in, will be Poisson with expectation N of T times W bar, where W bar is just the mean fitness across offspring of random matings among these people. Okay? So, now offspring of individuals I and J, we're using the infinitesimal model, so they're going to have a mean trait value given by the mid-parent value, and a variance. Well, if we had haploid parents, it'll be this, and diploid parents, it'll be that. This is the infinitesimal model that we used before. And the fitness, if we take in the trait value Z, we said fitness will be e to the beta Z, so this W bar will take this form if the parents are I and J. So this is just, I've got a normally distributed random variable with mean Zi plus Zj over 2, and variance we've written as Vij, so this is this quantity here. And this is just saying what's the expectation of e to the beta Z if Z has that distribution, and it turns out to be this quantity. Okay. All right, so that tells us how our population will grow. Now, what we're going to do, we're going to take a very, very crude model, but surprisingly, it's going to reveal a lot of what Nick just showed us through mathematics. So we're going to assume that the trait distribution across the whole population is Gaussian, but I emphasize yet again that is not a consequence of the infinitesimal model, but it's probably a reasonable approximation if that beta, if that strength of selection isn't too great. Okay. And as a first approximation, we're going to suppose that the population size and the trait mean and variance just evolve deterministically. We'll put some more noise in a moment. Now, each diploid migrant, this was coming back to Matthias's point, carries half of the genetic variance in the source population. So actually, rather modest rates of migration into a small sink population can nonetheless maintain very high genetic variance. So there's something for that selection to be acting on. And we're going to assume, and this is a gross assumption, we're going to assume that the identity is 0. We can be more sophisticated, but the formulae get really quite horrible, and even we chose to put them in the appendix of our paper. So we're going to forget the identity, and we're just going to suppose that within family variance is always this V star, irrespective of where the parents came from. So it might be the parent was a migrant, and the one parent was a migrant, the other parent had been already inside the sink population. It might be they're both from within this population, but we're always going to assume that the within family variance is V star. Okay, so this is very, very crude. And recall that in our previous model of variance, so when we first introduced the infinitesimal model, we said, well, the variance will then be twice V star. All right. And so what we're going to do is just set up a recursion for the way that the population size and the trait mean evolve with time under this model. So this is just a reminder that this was the distribution of traits across the whole population is going to be normal with some mean Z bar and twice V star. Half of this comes from within family variance and half from the variance across the whole population. And so this mean fitness, we just substituted takes this value. So after reproduction, what we said before was that this is the number of descendants, the mean number of descendants of the population that was already there, and we add an additional M migrants to that. And then what happens to the trait? Well, the M migrants all had trait value on, the mean trait value of my migrants is ZS bar, that they came from the source population. And the mean trait value for my offspring here, well, they've been adapting. So they're going to be sampled according to the fitness. So the mean trait value among the among these guys, among the N of T e to this, is going to be given by this expression. So they're sampled according to their fitness. So this expectation here, what this is saying is with respect to the distribution of trait among offspring before selection, so before we do the pruning, and we calculate it just by differentiating this W bar. And if we do that and just substitute, so these are the equations that, this was the equation that we wrote down before, this is how the population is growing, but then substituting for the mean trait value, we arrive at an expression like this. Okay. So, now, it turns out to be convenient to use different parameters. So you'll notice that, so Nick set this twice V star equal to 1 in his simulations, and this is his beta. So this beta is this key parameter that he kept using. And we are going to normalize so that we're interested in, we normalize the total population size by the number of migrants in each generation, and we use standard units for our trait value. And then the equations are just a little bit simpler to handle. And so the top one is easy, right? So that's just going to be that in generation T plus 1, this quantity, well, 1, because M over M is 1, and then N of T, N over M is 1, and then we have this expression. And then our traits, so if we're just normalizing, so we're going to subtract ZS bar from both sides and divide by this to turn into standard units, then we will obtain a recursion of this form. And as a reminder, here's my WS again. Here's my mean growth rate of the source population in the new condition. So if I take an individual from my source population, what's the sort of average growth rate of an individual with the, which is taken from the source population? Well, ZS bar was the mean, and remember we had this variance twice V star among the source population. So the equation just looks a bit simpler. I don't really expect you to absorb these equations. I just want to say that it's not really rocket science. Okay, so there are those equations again. And what we're going to observe is that if the mean fitness in the source population is high enough, this is what we saw in Nick's pictures, then actually the population size and the trait mean are both going to increase together. We're getting a population which is going to increase regardless of the migration rate and grow without bound under this model, though obviously we can modify things to put in some sort of population regulation to prevent that. if the mean in fitness in the source population is too low, then what we're actually going to see, and we will solve these equations in a moment to see them, we see two equilibria, one stable and one unstable. And what can happen, as Nick's last slide showed, was the population might find it very difficult to grow, no matter how big the migration rate is, because it's being pulled back by these unfit migrants who are poorly adapted to the new population, and we get ourselves a sink population. Okay, so let's see that in numbers. So what I want to do is just find the equilibrium of this, and that'll tell me my critical values, and that's surprisingly easy. So this you can just rearrange to see that at equilibrium, it must be that y is equal to alpha times n minus 1. Sorry, that's what this one here says. And then just substituting, so if I substitute this value of y into this expression here, I end up solving an equation of this form, and actually that just gives me a quadratic equation in n. So I need that n is equal to f of n, that's what looking for a fixed point here says, and I need that f primed of n is equal to 1, and that yields me a quadratic in n, and you can just find the solution and write it down. Now, we've lost track now of what the original parameters were, so let's put this back in our original units. And if we put it back in original units, we see that the critical value for the population size above which things behave well is given by this expression, and the critical fitness, so this is this critical fitness in the source population above which things adapt well and have a good chance to evolve and establish quickly, is given by an expression of this form. Okay, now what do we want to say about this? And here, so this is this growth rate, this is this critical growth rate parameter. And what Nick showed you, so if we look at this expression, and suppose that beta is small, so he'd normalize this to be 1, and let's suppose beta is rather small, then if we actually substitute for this critical value of beta times zs, we find it's about minus twice alpha, that's minus twice beta, so that's minus beta times, and this is a standard deviation in the source population. Okay. So that's telling us, again, we're revealing that the critical value above which we will see a good chance of establishment is determined by just how fit a typical individual is coming out of the source population. And this corresponds exactly to the sort of numbers that Nick was pulling out, where he said, well, I can be 2 standard deviations below and everything's just fine. Okay, so we can solve everything. Right, now, but what we really wanted to do, so this is quite nice because it gives you a very simple way to see that you will or you won't get stable equilibria. But what we really wanted to do was to incorporate some noise. And there are 2 things we can do. We can try to track the probability of identity, and as I say, we do that, and it doesn't make as much difference as you might expect, partly because the variability in the population is maintained by migration. But what we thought we would do instead was introduce some demographic noise, so introduce some of the randomness just due to the reproduction. And to do that, it's convenient to first of all make a continuous time approximation. So here were our discrete time recursions, just back in our original units again. And what we're going to do is we're going to suppose that, I mean, we're thinking of beta as a rather small number, so we're going to take this quantity to be small. Remember, V star in Nick's simulations was set to be 1/2, so if beta's small, this is certainly small. And we're going to ignore terms of order beta squared V star. Now, it turns out, actually, that it's very easy to write down the wrong equations for approximating these recursions by a continuous pair of ordinary differential equations, and indeed, these are the wrong equations. Initially, we didn't notice that there should be a factor of 2 here. There's not a factor of 2 there, and there is a factor of 2 there. And so we put the factor of 2 in, and then we thought, oh, rats, actually, we also ought to have adjusted this migration rate. And then the formulae get really messy, and no one wanted to redo the simulations, and it was Christmas, and I wanted to go home. So I'm afraid that laziness led us to deciding that since this was such a crude model, fussing about whether the error we were making in approximating this by differential equations was beta squared times m plus n or beta z bar m plus beta squared times m plus n was not worth it. So this pair of equations isn't quite the pair of equations that we should have written down, but it's a reasonably good approximation to this discrete time recursion, at least if beta z star is small. Okay, and then we wanted to add random perturbations, and we already saw how to do this yesterday. We saw how you can combine demography and genetics, and in essence, in our crude approximation, all we are going to do is add a Feller noise to the population to indicate that we've got a branching process going on, and so that's what this notation is meant to convey. And we want to add a Wright-Fisher noise to the trait because we've got the random mating within the population, and this is, of course, the variance of the individuals that we pick, and a 1 over n, so the standard thing that you would expect from a Wright-Fisher noise, that the variance of the trait value divided by the population size. And if we also introduce a potential, it turns out we're going to be able to solve things rather exactly. So I'm just going to use u to denote this expression. And then our equation for dn dt, before dn dt was just m plus b to z bar times n. And I'm adding this noise term, but it turns out it's convenient to write that as n du dn plus zeta n, because then that's going to give me a form for a stationary distribution for this equation, where u is this slightly complicated looking expression. Similarly, dz bar by dt, well, here was our equation for dz bar by dt before, the deterministic equation, continuous time deterministic equation, and we've added on a kind of Wright-Fisher style noise term, and we can write that in terms of our potential as this plus z to z bar. And because of the very special form of the deterministic parts of those equations, we can write down, if it exists, an exact expression for a stationary distribution. So if there were a stationary distribution, and I choose my words carefully, then it would be proportional to this expression. So this comes directly from integrating this guy here, right? We exponentiate this guy here. Oops, there we go. Now, there isn't a stationary distribution because we've allowed our population to grow without bound. So we know that actually this thing will eventually blow up. But nonetheless, one can expect that this should be a reasonable approximation to the density near to a stable sink. So if there is a stable sink, as Nick was explaining, which you might get when there's a lot of migration, then this is roughly what the density should look like close to that stable sink. And notice there are three terms. So we've got this, which increases because of migration, because migration, if you increase the migration rate, you are getting a lot of new individuals coming in. That is going to boost the population at some level. This is selection, saying if my mean trait value is big enough, then I'm going to grow. That's my growth rate. That's good. But then we have this gene flow pulling us back towards the source population. And that's the answer to Anton's question, that because I'm more likely to breed with somebody who's poorly adapted, I get dragged back. Okay, held back by my husband.
Will this be exponential and the immigration is just linear? Will this be a natural, really pulling? Will it be strong enough? Yeah, really.
Yeah. Which is why when m tends to infinity, Nick shows that it takes an infinitely long time for your population to escape from this sink and actually establish properly. Okay. So we can say a bit more about the stationary distribution. We can write down if we fix the population size, then the trait mean will be normally distributed, but we've kind of forced that upon it. And this is what it looks like. And this is a deterministic equilibrium in which selection is increasing the trait mean, gene flow is opposing the trait mean. Same statement again. And if we integrate over z bar, we can also see how the population size should look, and the population size will be of this form. And what we see again is that if m bigger than a half, well, that's not too much to ask. We want a lot of migration or our model's going to break down. So if migration isn't ridiculously small, if in the source population, our ZS bar, so this is the mean fitness in the source population, is less than about 2 standard deviations away from the mean, so the positive growth rate. So if it's 2 unfits, this is the -2 that we had, then this distribution has got a peak at low density. And for that peak, if you go back and you say, well, for that value of n, what's z bar going to look like? Well, z bar is negative. So again, we actually see very explicitly in our formulae the sink population that we've seen. So we've got this metastable sink population with a negative mean fitness, which is only being maintained because of the gene flow. So in spite of the simplicity of the model, we're able to recover the kind of picture that Nick was showing us. And I think it's back to you, Nick, for some more pictures.
Yeah.
There's your first picture.
Here we are. So these are just some simulations to show, rather to our surprise, that all these very shaky kind of approximations do work, at least in some parameter regime. So we have this sort of diffusion approximation for the joint distribution of the mean of the trait and the population size. And first of all, look at this situation where we have a bifurcation of the deterministic model so that the population may be stuck in a sink state. In the stochastic version, of course, eventually it will escape, but it will spend a very long time at an equilibrium where it's being pulled back by migration despite its inherent tendency to adapt to increase its growth rate. So here we have 10 individuals per generation. We have a source population minus 3 standard deviations below the critical growth rate. Rather weak selection, actually, to get the things to fit nicely. All these things are approximations for weak selection. And everything's scaled to 2v star equals 1. I should point out something which is a very slight subtlety that actually I haven't said before, and that is that all of this modelling assumes a V star, a segregation variance, within the sink population. And that will have been reduced by inbreeding. And so what we're doing is taking this V, scaling relative to this V star, it will be lower than the V in the source population. That's why we call it V star. So just to go through this is the distribution of population size. This is in the simulations. The red line is the prediction, conditioned on the V star in the population. This is the segregation variance within the sink population, which we are assuming is constant, independent of the actual numbers in the sink population. And in fact, that's a surprisingly good approximation. So this is the real key to why this stuff works. Essentially, the population is fluctuating up and down, but there's enough mixing and enough, if you like, of a buffer in which the segregation variance is being held within diploid individuals. And it's that, if you like, smooths out fluctuations in variance and means that it stays constant, and our approximations for V being constant independent of N is kind of okay. This is the mean as a function of N. The dot is sort of the distributions of the simulations, and this curve, the solid line is the mean trait value conditional on N. It's lower when the population is smaller because it's being pulled back more, relatively speaking, by the migrants. If you've got a population of 20, you've got 10 individuals coming in every generation, a third of the population is being replaced. You're being pulled back to essentially the -3, the value of the source population. If the population's up in the hundreds, it's doing better, but it's still being pulled back. Notice that all these growth rates are strongly negative. It is in a sink situation. It's always going downhill despite migrants. Nevertheless, it can get up to a reasonable number. And then this shows the mean inbreeding in the population as a function of N. And the inbreeding is greater in a smaller population, not surprisingly. But in this sort of regime, it's not varying too much, and therefore the variance realized is not varying too much. Okay. So I'll just finish by extending it in an extravagant way. It's slightly embarrassing that at some point the whole thing blows up. And in order to prevent that, you need two things. You need density regulation. You need to have the growth rate decrease, let's say linearly with population size. That isn't enough by itself, because if the population can keep adapting, under directional selection, the trait will keep increasing, the growth rate will keep increasing, it would still blow up. You have to have both density regulation and some kind of stabilizing selection. So now this trait is moving to some new optimum. So what we're supposing is that initially the trait is under directional selection, that's the whole analysis so far, but now we're saying, well, realistically, this trait moves to a new optimum, let's say an optimum of 5 units or whatever. So this just shows that you can still make predictions. You can extend the diffusion approximation we had before to include this and to write down the joint distribution of N and Z bar including stabilizing selection and density regulation. So here we have the distribution of n. This is the sinc state, and this is the new established state, established at a very large number. This is the expected trait mean as a function of n. It increases with n. I mean, if you squint, then it's not too bad an agreement. It kind of goes up in about the right way. The variance is in the simulations in the black line. The variance is lower when you're in the sinc state than when you're in the established state, but it's not a huge difference. And actually, the prediction there is not too far off. And again, the degree of inbreeding doesn't depend too strongly on n, which is why this sort of diffusion approximation kind of works. Okay, so summarizing all this, if you have a single individual coming in from a source population which has a negative growth rate under the new conditions, then it's got a reasonable chance of establishing if, let's say, the mean of the source population is no more than 4 standard deviations below the threshold. If you have continuing migration, then that can prevent adaptation in the new habitat and produce a kind of sinc state from which it's difficult to escape. It will eventually escape, and if it does so, it will actually be partly reproductively isolated. So one can think of this as a kind of speciation model, and we actually have worked out, and it's somewhere in Appendix 6 of the paper. We worked out the strength of reproductive isolation, because now you've got 2 differently adapted populations, and a migrant coming in will actually leave very few offspring because its offspring will be intermediate largely and will also be much less fit. So you could think of this as a kind of a model of speciation as well as a model of evolutionary rescue. So I'd just like to end by saying I think it's actually a wonderful demonstration of the power of very shaky approximations. So, okay.
Great, thanks for that wonderful tag team talk. Again, there's plenty of time.
Yeah, John?
Questions. So please wait for the mic to arrive when you ask your question.
Thanks. Have you thought about the effect of increasing the level of selfing? I would guess there could be a couple of different effects, and one of them, which might be interesting, is that individuals who end up being fit in the new environment could produce offspring just with themselves,
yes,
and not be swamped
yes,
so much.
Yes,
so.
That's it. And there's also a sort of automatic advantage of selfing, which are kind of like the twofold cost of sex, analogous to that. Again, a Fisher idea. On the other hand, there's increased inbreeding. So it would be very interesting to look at the sort of the balance between increased inbreeding versus, if you like, reduction in gene flow by mating with the other bad individuals. I think we'll sort all this out very soon, but we'd like to include inbreeding depression as well, because once you start talking about varying selfing, the referees are going to say, what about inbreeding depression? So we need to do that. Yeah.
Other questions?
A question about the effect of selection on inbreeding. Until what level of selection can you expect that the model can sustain itself, and you can still I'm sorry, I can't find my words. You can still approximate f to be 0, or not. I mean, not too high.
Yeah, I think it was a little bit misleading. Probably shouldn't put it on the slide. That in the latter part, we weren't quite assuming that f was 0. We were really assuming f was constant. And what we were doing is saying, in this population, you have a sort of an average segregation variance. And what we're ignoring is the fact that obviously the segregation variance when you mate with a migrant is going to be different with a mating between 2 natives. We just ignore all that. But we do allow for some average segregation variance, which will be influenced by the level of inbreeding. Yeah.
We didn't completely ignore that, actually.
No, there was a,
we did
yes.
reproductive value stuff.
Yeah.
Getting reproductive isolation. Yes. You can extend this almost indefinitely, but the problem is that it gets harder and harder to deal with. But the basic model is good as long as your pedigree is not too distorted. And the fact is that as soon as you've got a reasonable level of migration, you're really keeping a very large degree of variability in the population.
And that's actually something quite surprising. You'd think that the whole thing would be dominated by extreme inbreeding, but actually with even a few migrants coming in every generation, you maintain quite a bit of variability. Yeah. And then all these QG quantitative genetics approximations work pretty well. Yeah.
So coming back to the inbreeding depression, so how would you include it in the model?
We will know by Christmas,
okay.
I think. Alison?
We'll write it down by Christmas. And we had an approximation here, which was very crude.
I mean, the full infinitesimal model, including dominance, which you need, would mean tracking the additive component and the dominance component of the trait. And it would mean allowing for the fact not just that you have to define the dominance variance, that's the variance of the dominance component, but also you have to allow for another parameter, which is the regression of trait value on inbreeding, and that's the inbreeding depression. So we've now got an effect on the mean of identity by descent. Right, so we have to include that. And we can sort of see how to do it, but it's not been written down.
Yeah, well, and also you can't do it in terms of things you could actually measure, apart from in your...
In my fantasy world, yes.
Fantasy world.
Yes, yeah.
It's not very ethical, fantasy world.
Well, no, I mean, we do have ways of measuring dominance, variance, and inbreeding depression. Those are measurable. And then given those, we can predict what will happen. This is classical quantitative genetics. And in fact, the job is not so much to get anything new. All this stuff exists in the classical QG world. But it's to justify it in terms of an infinitesimal limit. Yeah.
Other questions? I've got a very naive question, especially since I'm more ecological in my background. But you could treat this as a branching process if it was asexual populations with a continuous trait. Yeah. And you have those types of branching processes with a continuum of traits possible. Do you have people looked at that, and do you get a very different answer than what you'd be finding here?
So I guess this must have been done somewhere, but it's a little bit tricky because you've got to, would you include mutational variance? And if you don't, then it's simply individuals who are just...
mutational variance.
And if it's a branching process, then and there's no mutation, then of course individuals just, it's trivial. You've got to have mutational variance in. I think, you could do that. It would be an interesting calculation. Yeah.
So actually, Keston had an attempt to put together a branching process model, which for a while we thought would really work here, where you've got branching for diploid populations. The cases for his model when you can calculate things are precisely the cases which don't fit here. So if you decide that two individuals reproduce and their reproductive success might depend on both types, but the type inherited by the offspring is one extreme or the other, then you can calculate things very explicitly in Keston's model. But in our kind of framework, it just doesn't work at all.
Correct. But I was thinking about the asexual case, right? Where you don't have to worry about the frequency.
Yes, you could do that.
Yeah. Any last questions? Yeah.
Just exercising.
I need it.
It's actually more a comment regarding the asexual populations. There's a paper by Rustam Antia and Bergstrom where they actually look at it in the context of a invading infectious disease, starting off with an R naught less than 1 and then going to an R naught greater than 1. And basically they look at it in the context of a multi-type branching process. And they basically, the main conclusion of that, I think it was a Nature Science paper from like a decade ago, basically had the result being that your initial kind of R naught in the source pool matters, and the closer that is to 1, the more likely is that probability of emergence as one would anticipate. But you don't have this kind of pull of the migrants, right, back.
But that comes out of sexual reproduction.
Right, exactly.
That's crucial.
Exactly.
Yes.
Any final comments or questions? Okay, if not, let's thank Alison and Nick for a wonderful talk.